section in chapter 11, which is areas and volumes of similar solids. So if we have learned anything this semester, I would say similarity has been a big one. And here we're talking specifically about solids, which is referring to the three-dimensional figures we've been studying in chapter 11. So a lot of our previous knowledge of similarity is going to come into play, and then we're just going to expand on it here. So looking at, are these two figures similar? We said before, when it comes to similarity, we have to have figures that are the same shape. So they have to be same in their shape, and they have to have proportional sides. So I would say the proportionality thing obviously still plays a big role, but we're going to just change this a little bit. And we're going to say they have to be the same figure when we're talking three-dimensional, which means you can't have a cone that is similar to a pyramid or something like that. So in this case, we're looking at two rectangular prisms. So they already have that same figure thing going for them. And we check that their sides are proportional. Whenever we check sides, remember we always look at corresponding sides. So if I look at this edge right here being 2 meters, this one being 4, that is in a ratio of 1 to 2. And if I look at each of the other corresponding edge lengths here, they are all in that ratio of 1 to 2. So let's first look at this smaller figure and calculate the surface area, because this gives us a good chance to review. You can draw a net here for this rectangular prism. That's totally fine. Or we can remember for prisms, we take the perimeter of the base times the height of the figure plus 2 times the area of the base. So the perimeter of my base, if I use the bottom rectangle here, is going to be 2 plus 1 plus 2 plus 1, so 6. The height of my figure, we're going to use that side length, that edge length of 3 along the side here. And then plus 2 times the area of the base, which would be 2 by 1, is 2. And so the surface area will be 18 plus 4, or 22 meters squared. If I'm finding volume, then I would take area of the base times the height of the figure, which is similar for almost all of my figures, that I take area of its base times the height of the figure. With pointy figures like pyramids and cones, we just divide that by 3. So not too bad of a formula there. Area of the base, again, will just be that 2. Height of the figure will be 3, so it looks like we have 6 meters cubed. So when we go and take a look at our larger figure here, I won't write out the formulas again, but the surface area of this perimeter of my base would be 12 times the height of my figure 6 plus 2 times the area of the base, which is 4 by 2, so 8. So it looks like we are taking 72 here plus 16 here, which gives me a surface area of 88 meters squared. For the volume, area of the base is still 8 times the height of the figure 6 gives me a volume of 48 meters cubed. Okay, so we have surface area, we have volume. So let's take a look at the ratio table created with this. Now, by checking the corresponding sides, we found the similarity ratio. Each of those corresponding sides was in a ratio of 1 to 2. So whenever you're checking for that similarity, obviously you're finding your similarity ratio, making sure it matches up. For my surface areas, I got, for the smaller, a surface area of 22. And for the larger, I got a surface area of 88. Well, let's analyze that. That reduces 22 to 88, reduces to 1 to 4. Cool. So that's nice. I think we see a little bit of a pattern there. If we take a look at the volumes, the volume of the smaller, I got 6. The volume of the larger, I got 48. How does that reduce? Well, 6 goes into 48 8 times, so it looks like we have 1 to 8. Cool. Here's our ratio table. Now, this is where our previous knowledge comes in, because if this is A, this is B, it looks again like my surface area is going to be that A squared to B squared, like we studied in chapter 10. This is, after all, just an area. So the nice part about that is this totally carries over with what you knew from chapter 10, because an area ratio is always the squared version of the similarity or side ratio. Now, adding on to this with my volume ratio here, it looks like if I'm evaluating A and B being 1 to 2, that I can cube each of them and get A cubed to B cubed 1 to 8. So this is a nice handy property when it comes to making our table here, that I have A to B, A squared to B squared, A cubed to B cubed. And if we keep in mind the fact that finding an area always leads to having units that are squared, and finding a volume always leads to units that are cubed, this makes a whole lot of sense. This seems pretty logical that our ratio table would look like this, and that if I am finding the volume of a larger figure, that I would cube the similarity ratio or the side ratio. So let's do an example with some not so nice numbers. You will do a couple problems like this today with nicer numbers for sure. Okay, but we're going to take a look at an example of how to use this. Whenever we're doing these problems, we're going to do them in 2 steps. The first step here is we have the lateral areas of 2 paint cans, which lateral just means this, this area around the lateral face. It's still an area, which means we have part of our surface area ratio here. That's going to be step number 1, is using the surface area or lateral area ratio and then creating the rest of the ratio table. That's step number 1. Step number 2 then is going to be that we have the volume of the smaller right there, and we want to find the volume of the larger. So we're going to do that last. So let's do our ratio table first. We know that we have 1019 to 425, or I'm going to flip that and I'm going to do smaller to larger. I like to keep the consistency of smaller to larger. Otherwise, I may set up my proportion wrong. So first thing I would want to check whenever doing these is if I have these numbers here, I want to, in my calculator, do 425 divided by 1019, and I want to do math frac to see if this reduces at all. Okay, so check for reducing, because it might give us nicer numbers to deal with. And the way we do that is in the math menu of our calculator and option 1, which is, keeping that as a reduced fraction. Oops. This one, like I said, not so nice numbers. So this one doesn't reduce at all, but check today for the ones that you work with for that reducing, because you will have some nicer numbers with that. So this is A squared and this is B squared, and unfortunately, they're not the nicest. And in fact, when I go to work backwards here to get my similarity ratio, I want to take the square root. So I want to find A and I want to find B, and these numbers don't come out to be the nicest square roots. So if I take the square root of 425, I'll go ahead and write it here as a reduced fraction, or I'm sorry, as a, not as a reduced fraction. I'll write it here as a rounded decimal. But I don't want to use that rounded decimal because we've talked about the problems that intermediate rounding can cause. So I want to actually take the square root of 425, and I want to use my STO, my store button, and I want to store that as alpha A. So store that 20 point ... as alpha A. And then what I'm going to do is the square root of 1019, chalk also does not come out to be very nice. So I'm just going to directly store that as alpha B. So I'm going to type it into my calculator, but then I'm just going to automatically store that as alpha B. Okay. Now, because those are not so nice numbers, over here when I go to calculate my volume ratio and I'm cubing them, also, I'm not going to get nice numbers. So I'm just going to write here, instead of the decimal, that I took the square root of 425 and I raised it to the 3rd power. And that I took the square root of 1019 and I also raised that to the 3rd power. Instead of writing a decimal, which, yes, I know, decimals might look a little nicer, but at least I know that this is the exact answer and not the approximate answer. So that was step 1 right there. I now have my ratio table, and I want to move on to step 2. Step 2, I know that the volume of the small is equal to 1,157 centimeters cubed. And I want to figure out the volume of the large. I don't know what that is. But again, we're going to bring back what we've learned in our previous units, and we're going to write a proportion. Okay. So this is why we needed that ratio table, is we want to write a proportion. And no shock here, if I'm trying to find a volume, I am going to use the volume ratio in my proportion. That's why I wanted to do all of this as step one, so I could make sure that I use the correct ratio. So I wrote smaller to larger here. I wrote that a cubed to b cubed. And instead of writing it out like this, I'm literally just going to write a cubed and b cubed, because if I stored those in my calculator already as a and b, then I'll be set to go. And my other half of my proportion will look like the volume of the smaller over the volume of the larger. So 1,157 over my unknown x. Now I'm just going to do my cross multiplying with those variables. On the one side, I'll have 1,157 times b to the third. On the other side, I will have x times a to the third. And in order to solve for x, I'm going to divide out that a to the third from both sides. Now, again, if you've done the work to store in your calculator, this is exactly what you're going to plug in. You're going to use the shortcut of hitting your alpha button and then your y equals button to bring up that shortcut menu for your fraction. Or you could just do them as two operations. Do the top part multiplication here first, hit enter, and then divide it by a cubed. That's totally fine. I'm going to plug exactly this into my calculator though. 1,157 times alpha a raised to the third power, and then in the denominator, alpha b to the third power. And that gives me, oh, I'm sorry, I flipped it. I totally said that backwards. Okay, so 1,157 times b to the third, let me do alpha b there instead, over alpha a to the third. Okay, sorry, double checking there. Okay, so what I got when I solved for x here is I got 4,295 now I'm going to round, okay? I try not to use any intermediate rounding. Now I'm going to round to 2 decimal places and get 48. And this would be in centimeters cubed. So this right here, we are saying is the volume of the larger. And let's just check if that makes sense. I mean, the volume of the small one here was 1,157. So it would make sense here that this is going to be larger, obviously. That's a great way to just kind of check and make sure that that makes sense, okay? With our numbers, these ones weren't as intuitive, but when you get nicer numbers, like if you had 1 to 2, 1 to 4, 1 to 8, then you would be looking for a volume that's about 8 times as large, right? So just make sure your numbers are making sense. And if you have any questions about this, obviously feel free to let me know.